Today we're going to talk about the titrations, and especially about the volumetric analysis. So that's going to be the topic of today's lectures. So this titrations method that we are going to introduce today, they are often called titrimetric methods. Okay, and this is actually a quite large group of quantitative procedures that are widely used in analytical chemistry to determine acids, bases, oxidants, reductants, metal ions, proteins, and many other species. Okay, titrations, the simple titrations, okay, can be used to determine the composition of superconducting materials. So that's quite impressive. Now, all these methods, what they have in common is that they are based on a reaction on a reaction between the analyte. So this is the species we're trying to determine concentration, and a standard reagent that is known as a titrant. So the reagent for which we do know the concentration, this is called a standard titrant, or titrant in short. The reaction that we're going to use for a titration has to be of known stoichiometry, and of course it needs to be reproducible. There is few more requirements that we're going to talk about as we go along. So what do we use in these methods? What is used to calculate the concentration of the analyte is the volume or the mass of the standard reagent or the titrant. Okay, so from that volume or mass, we calculate the moles of the titrant, and then we use the reaction, the stoichiometry of the reaction, to get the moles of the analyte. Okay, so that's how we go from the standard reagent to the unknown or the analyte. So there are two types of these titrimetric methods. In volumetric titrations, we use the volume of a standard reagent to calculate the concentration of analyte. And in gravimetric titrations, we measure the mass of the standard reagent. And from that mass, we can calculate the moles, and then from the stoichiometry of the reaction, we can calculate the moles of the analyte. Now, there are also titrations in which you measure the quantity of charge that is required to completely consume the analyte. And if that is the quantity that is measured, then we talk about coulometric titrations. Okay, so it all depends on which quantity we measure. If it's volume, it's volumetric. If it's mass, it's gravimetric. If it's charge, it's coulometric. Okay. Now, in all titrations, the point of chemical equivalence. So this is the point where the amount of the reagent and the amount of the titrant are chemically equivalent. Okay, so that will depend on the stoichiometric of the titration. So that point can be measured experimentally, and if it is obtained experimentally, it is called endpoint in a titration. Okay. Now, it's usually signaled by, and we usually use an indicator to determine the endpoint of a titration. But there are many different methods for determination of this endpoint. Now, the progress of the titration is typically shown using a titration curves. Okay, or titration curve. So this is, in general, when it comes to details, we will almost exclusively deal with volumetric titrations. So your standard reagent, we will use the volume of the standard reagent to determine the concentration of the analyte. So in volumetric analysis, we measure the volume of a known reagent required for a complete reaction with analyte, okay? And from that volume, and again, the stoichiometry of the reaction, we calculate how much analyte is in the unknown substance. Now, the whole procedure relies on adding a small increments of the titrant, or this standard titrant, to the solution containing analyte until the reaction is complete. So that procedure is called a titration. So the titrant, since we use the volume of the titrant, we need to determine the volume of the titrant that was added up to the end point. The titrant is usually in a burette. So this is a burette. It allows you to not yet. It allows us to determine the amount or the volume of the liquid that was delivered from the burette quite accurately. Okay. And the solution of analyte is usually kept in a Erlenmeyer flasks. So the typical setup for carrying out these titrations is shown here in this picture on the left. Okay. So the apparatus consists of a burette, okay, that holds the titrant, burette stand that keeps the burette in this upright position, and we can deliver the liquid from the burette using the stopcock. So that was better seen here. So this is the stopcock here. We just open it and close, and it allows you to deliver less than a drop of a titrant at a time. Okay. So this way we can measure the volume quite accurately. Now, the burette stand should preferably has a white porcelain base in order to provide an appropriate background for viewing the indicator change, because the indicator that we use to determine the endpoint, the way it works, it changes color most of the time. So at the endpoint, at the end of the titration, you will see a color change. And in order to see it better, this base should be white. Or since most of our stands are kind of old, to improve the visibility, you can always put a small piece of paper under the Erlenmeyer flasks to help you view this indicator change. Now the flask that is shown here, okay, contains the solution of the analyte. Now we need to know precisely the volume of the solution of analyte, okay, because we're trying to calculate the concentration of the analyte. So the concentration is number of moles that we will obtain from the titration per volume, right? So we need to know this volume quite accurately, and it needs to be measured before you put it in this Erlenmeyer flask for the titration. Now, we usually deliver this solution of analyte into this Erlenmeyer flask using a pipette, a transfer pipette, which allows you to determine the volume also very, very accurately. Okay, so let's go back to the burette for a second. So the burette is a precisely manufactured glass tube with graduations enabling you to measure the volume of the liquid delivered through the stopcock, the valve, okay, which is located at the bottom. So that's the stopcock. Now the numbers on the burette, they increase from top to bottom. So on the top of the burette there will be 0, that's 0 milliliters, and then going down these numbers increase. Okay. So a volume measurement is made by reading the level before and after draining liquid from the burette and subtracting the first reading from the second reading. Now, these graduations on the graduations on the burette. Okay. Now the burettes do have a class designation. So the class A burette, or in general class A glassware, is the most accurate glassware. Okay, so these graduations on the class A burettes are certified to meet the tolerances that are given in this table below. Okay, so depending on the volume that was delivered from the burette, the tolerance goes from plus minus 0.01 milliliter to plus minus 0.1 milliliter. So as you increase the volume that is delivered from the burette, the tolerance also increases, so that measurement is a little bit less accurate. So for a typical 50 milliliter burette, okay, typically the burettes they can hold 50 milliliters of liquid. So if the reading of a 50 milliliter burette is 32.5 milliliters, okay, so then the volume will be 50 milliliters, right? We're using 50 milliliter burettes, and the tolerance for this burette, if it is a class A, is plus minus 0.05. So the true volume, okay, the true volume can be anywhere in the range 32.45 to 32.55, right? If you are at 32.5, then the tolerance is plus minus 0.05. So, that would be the true value of the volume, which is within this manufacturer tolerance for a class A burette. Now, let's go back a little bit to the very basics. So when you read the liquid level in a burette, okay, your eye should be at the same height as the top of the liquid. So this is the top of the liquid, right? Your eyes, whenever you try to read this volume, your eyes should be at the same level. If your eyes are too high, the liquid seems to be higher than it actually is. So you will introduce an error which is called parallax error. If you're trying to estimate the volume without keeping your eyes at the same level as the liquid. So if your eye is too low, the liquid will appear also too low. So this error that occurs when your eyes are not at the same height as the liquid is called the parallax error. Now the meniscus, right? So the liquid, the solution in the burette, it forms this meniscus, and this is the curved upper surface of liquid in a glass glass burette. So water, if you have an aqueous solution, it will have a concave meniscus, okay? Because the water is attracted to the walls of the burette, and it kind of clings and climbs up on the sides. And the center of the meniscus is little bit lower. So when you read the level of the liquid, you should be reading the center of the meniscus, okay? Sometimes it might be helpful to use black tape on a white card as a background for locating the meniscus. So you just put a short piece of a black tape on a white paper, and then you try to align this black tape with the bottom of the meniscus. Okay, so that might help you to estimate or to read where the meniscus is. All right, so if you have worked with highly colored solutions, you might have noticed that these solutions tend to have two meniscuses, I guess. You'll see like two or double meniscus, okay? Let me put it this way, since I don't really know what is the plural of meniscus, okay? But these high colored solutions will have double meniscus. So when you read the burette, always you can use either one, and as long as you're using always the same meniscus for your reading, you will not introduce too much of an error. So it's important to be consistent, okay? And I did say that before, I believe, but always estimate the reading of a burette to the nearest tenth of the scale division. Okay, so on a 50 milliliter burette, the smallest graduation is 0.1 or 1/10 of a milliliter. Okay, so that short line indicates 1/10 of a milliliter. So when you read the volume, you're supposed to estimate the reading to the tenth of that smallest division. So that means you will be estimating the volume to the nearest 100th of a milliliter, okay, or two decimal places, and this will be the last significant figure. Well, the thickness of a graduation line on this 50 milliliter burette corresponds to about 2/100ths of a milliliter, 0.02 of a milliliter. So the difference or the volume between the top of this graduation line and the bottom in a 50 milliliter burette is about 2/100ths of a milliliter. Okay. So so to use the burette most accurately, you may want to consider the top of a graduation line to be 0, and then consequently the bottom will be 0.02, right, or 2/100ths of a milliliter, when the meniscus is at the bottom of the same graduation line. So a drop of a liquid from a 50 milliliter burette has approximately 5/100ths of a milliliter. Okay, so that's all these numbers, they give you some idea how accurate you can be with a burette. Okay. Now with a burette, it's possible to deliver less than a drop. Okay. In order to do that, you have to open the stopcock very, very slowly until you see that drop hangs from the bottom of the burette, and then close the stopcock and touch the inside wall of the flask with the burette. So this will transfer this less than a drop of liquid into the solution. And of course, you need to swirl it to make sure that the liquid on the inside walls of the flask comes into contact with the bulk of the solution in the Erlenmeyer flask. Okay, so this is the burette. Now the solution to be titrated is placed in an Erlenmeyer flask, okay? And before you start titration, you need to add the indicator. So the indicator is being added here using a dropper, and we usually require a few drops of an indicator. Always use the smallest possible amount of the indicator, because if you use too much, it's going to affect your results in many different ways. Changing volume, diluting. There might be side reactions with the indicator, so it is important to keep the volume of the indicator added to the minimum. Now, the indicator allows us to determine the endpoint of the titration. So this tells us when we're supposed to stop the titration. Now, during the titration, okay, so the last picture here on the right, it shows someone adding the standard titrant from the burette into the solution. So you can see that the titrant is added to the flask with swirling. Well, it's actually difficult to see it in a picture, but it's supposed to swirl the flask to make sure that if there is any liquid on the side walls, it comes into contact with the bulk solution, and it also helps mixing, so the reaction goes as it's supposed to go. Okay. Now, at the beginning of the titration, it is usually good idea, or you can add the titrant rapidly, so you don't have to add a drop at a time at the beginning of the titration, especially if you approximately know the endpoint. Okay, so initially you can add the titrant rapidly, and then as you getting close to the volume where you expect to determine the endpoint, then you need to slow down. Okay, you need to slow down, and if you are close to the endpoint, you should really add one drop at a time. And if you are very, very close, then you can try to deliver less than a drop. Okay, so by closing the stopcock with this part of the drop hanging from the burette, and then transferring it into the solution by touching the inside walls, and then swirling the bottle. Okay, so okay, so this is the procedure. Okay, some important things. The most important is because your titration will be as accurate as as accurately you can read the volume from the burette. Okay, so it's important to remember about this parallax error, how to read the bottom of the meniscus. So these are important considerations. Now, so how do we detect this endpoint? Okay, so when we should stop the titration. The endpoint in a titration can be determined using various methods, and here are listed 3 of them. Okay, but typically The indicator change includes the appearance or disappearance of the color. So your solution changes color at the endpoint. Or sometimes you can determine the endpoint using the changes in turbidity. So the turbidity is the measure of relative clarity of the water. So if you shine a light on your solution, if there is anything that scatters light, your solution will not be clear. Okay, and the less clear it is, the higher the turbidity. So that means more of this material. So the appearance of turbidity can also be used to determine the endpoint. But as an example, because next we're going to talk about the acid-base titrations. Okay, so the indicator used in the neutralization titration. So this is the reaction between an acid and a base. So for example, hydrochloric acid can be titrated with sodium hydroxide. Okay, and the typical indicator that is used is phenolphthalein. That indicator, the phenolphthalein, the indicator causes the solution to change from colorless to pink once the excess sodium hydroxide has been added. Okay, so this is very convenient because the appearance of the pink in your solution indicates the endpoint, and it's very easy to notice it. Okay, because if your solution is clear, then it's relatively easy to notice this appearance of a pink color. Now, we also quite often use instruments to detect endpoints, and the instruments respond to properties of solution that change in a characteristic way during the titrations. So these instruments might include colorimeters, turbidimeters, spectrophotometers are quite commonly used. So you can, for example, monitor the absorbance at a certain wavelength, okay? And then if there is a specific compound that absorbs at that wavelength, the absorbance will change. So that is quite commonly used. But we can also use temperature monitors, refractometers, voltmeters, and almost anything. But it always depends on what are you trying to detect. Okay, it depends on the reactions. So these indicators, they allows us to determine the endpoint. The endpoint, again, the endpoint is observed experimentally. Now, what we really need from our titration to determine is the equivalence point. Okay, so we are really trying to determine the equivalence point for a titration. The equivalence point, however, is theoretical point that is reached when the amount of added titrant is chemically equivalent to the amount of analyte in the sample. So the equivalence point is determined theoretically from the stoichiometry of a reaction. Okay, so if you have a reaction for the titration, you can, from the stoichiometry, you can determine the equivalence point. So if the stoichiometry of a reaction tells us that 1 mole of titrant reacts with 1 mole of analyte, then at the equivalence point, the moles of analyte equals the moles of the titrant. So that is the connection. That's how we can calculate the concentration of the analyte from the moles of the titrant. But to get the moles of the titrant, we need the volume in volumetric titrations. So we cannot determine equivalence point experimentally. We can only estimate in its position by observing some physical change that is associated with the condition of equivalence. Okay, so we experimentally measure the endpoint. So this change is the endpoint for the titration. So endpoint is determined experimentally using one of these methods that we that I mentioned on the previous slide. And then the difference, oh my, okay, here we are. The difference between the endpoint and the equivalence point is the titration error. So the goal in every titration is to minimize this titration error. So we need to have a way of the detection of endpoint that gives us very good estimation of the equivalence point. And for that purpose, most of the time we will employ a blank titration. So a blank, a reminder, a blank is a solution that contains no analyte. Okay. All right, so it's all about minimizing the titration error. Now, in order to understand the basis of endpoint determination and the sources of titration errors, let's take a look at example titration curves. So again, a titration curve is a plot of concentration-related variable on the y-axis, okay, versus titrant volume on the x-axis. So the reagent volume is on the x-axis, and on the y-axis we have some variable that is related to the concentration of either titrant or the analyte. Okay, so very to keep it close to the lab. Okay, so I'll use this acid-base titration, but for acid-base titration, the titration curve is usually a plot of the pH of the analyte solution versus the volume of the titrant added. Okay, and we generally distinguish these two types of titration curves, and that will gives us two general types of endpoints that occur in these stoichiometric methods. So in the first type, this is on the left, which is called a sigmoidal curve. The equivalence point or the important observation will be confined to a very small region, okay? So this region is typically about 1/10 or maybe half a milliliter of titrant. So the equivalence point or the end point happens after adding, well, 1/10 of a milliliter, or sometimes a little bit more, okay? This sigmoidal curve in which this concentration-related function of analyte or titrant is plotted versus the volume of the standard titrant. Okay, and the second type of curve is called a linear segment curve, and in this case we usually use some kind of an instrumental detection of the endpoint, but we do not perform the measurements in the vicinity of the equivalence point. The measurements near that equivalence point are avoided, and in this type of curve, the vertical axis represents directly instrument reading, so that's this, and the y-axis is the instrument reading, the x-axis is the again the same as in the sigmoidal curve, and that's the reagent volume. Okay. Okay, so the first type the sigmoidal curve offers the advantage of speed and convenience. So over the linear segment curve. However, the linear segment type might be sometimes useful, and the examples where the linear segment curve is more advantageous than the sigmoidal curve are when the reaction is complete only in the presence of considerable excess of reagent or analyte. So then we may resort to this other type of titration measurement. Okay. Now we will be dealing almost exclusively with the sigmoidal transition curves. Okay. So we need to discuss what happens, actually what allows us to determine the endpoint. Okay, what happens in the vicinity of the equivalence point, and why this can be used to determine the endpoint. So the reason, or what happens, is that the equivalence point in a titration is characterized by major changes in the relative concentration of the analyte and the reagent, the standard reagent or the titrant. Okay, so when we are close to the equivalence point, the changes in the relative concentrations of these two species are very, very large. Okay, and this is illustrated in this table. Okay, so the data in this table, and especially the second column, okay, it shows the concentration of hydronium ions, H3O plus ions, in a titration of 50 milliliters of 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. Okay. So what does it show? Okay. It shows you that initially we have just 0.1 molar solution of sodium hydroxide. Okay. So the concentration of hydronium ions is 0.1. Okay. The pH that we calculated for this 0.1 molar solution of NaOH will be 1, right? Now, it is not, at this point, it's not important how we calculate it. What's important is that in order to change the pH by a factor of 10, okay, we need to add the sodium hydroxide to this solution. Okay. So in order to increase the pH of this solution from 1 to 2 pH units, okay, so we're increasing it by 1 pH units, but that corresponds to the 10-fold increase in the concentration, because the pH is a logarithmic scale, right? So it requires almost 41 milliliters of sodium hydroxide needs to be added to 0.1 molar solution of HCl to increase the pH from 1 to 2. Okay. Now, another 10-fold increase in the concentration of sodium hydroxide, or corresponding decrease in the concentration of H3O plus, requires only a little bit more than 8 milliliters of sodium hydroxide. Okay. So to change the pH from 1 to 2, we need 41 milliliters. To change the pH from 2 to 3 in this titration, we need only about 8 milliliters, okay? And then if you look at the other numbers, to change the pH from 3 to 4, we need less than a milliliter, 0.89 of a milliliter, okay? So you can see that the same change in the pH as you're getting closer to the equivalence point requires less and less sodium hydroxide, the titrant, okay? In this titration, the end point or the equivalence point, since we're titrating 0.1 molar HCl with 0.1 molar NaOH, so, and we have 50 milliliters of 0.1 molar HCl, the equivalence point is going to be after adding 50 milliliters of 0.1 molar NaOH, okay? So, and the pH at the equivalence point will be 7, okay? So now, look, the pH of 7 is here, okay? But look at the change. If you add about 1/10 of the titrant, the pH changes from 5 to 7, and then adding another 1/10, the pH actually changes to 10. So by adding less than a milliliter of the titrant near the equivalence point, the pH changes by 4 or 5 pH units. Okay? By adding just less than 1 milliliter. So this is a very dramatic change in the pH. And that's what allows us to determine this equivalence point accurately. Okay? So again, this major change in relative concentration of the analyte and the titrant near the endpoint is what allows us to use the indicator. Why? Because the indicator in acid-base titration, right? It's a phenylephthalate, okay? So if we, okay, so let's take a look at a couple of examples of titrations, and let's start with acid-base titration, okay? So the endpoint in an acid-base titration where with phenylephthalate as indicator. So initially we have acid solution, that's our analyte, plus the indicator, which is phenylephthalate, okay? So this solution is going to be colorless, okay? Now, so this flask is clear. The solution is clear. So, and it will remain clear until you are approximately half a milliliter from the end point, okay? When you are about half a milliliter from the end point, you will see, upon adding a drop of a titrant, you will see this pink color in the solution, but it will turn pink for a while and then it will go back to the clear as the solution mixes. Did you have a question?
Chemistry behind that? Why it turns into another?
We will talk about this a little bit in more details, okay? But for now, it depends on the indicator, okay? Yeah. So for this one, the endpoint is when you see a persistent pink color, okay? For a typical acid-base indicator, okay, this color change occurs over approximately 2 pH units. Okay, so the pH of the solution has to change by about 2 in order for us to see the color change. Okay, now, but you remember from the previous slide, right, that the titration curve shows that when we are close to the equivalence point, the pH can change by 4 up to 5 pH units upon adding less than 1/10 of a milliliter. So this indicator changes color over 2 pH units, but that all happens within adding very little amount of the titrant. So we can use that. So we are talking about acid-base titration. Okay, so this is a reaction for a titration of hydrochloric acid with sodium hydroxide. So this is a neutralization titration. The product is water and some ions. Okay. So what are these indicators and why do they change colors, right, in acid-base titrations? In acid-base titrations, the indicators are usually weak organic or acids or bases, and their undissociated form differs in color from its conjugate base. So if you have a weak organic acid, the undissociated form will have a different color than the dissociated form, than the conjugate base, okay? And there are so many different indicators that actually works to our advantage because they will change or they will exhibit this color change over different pH ranges, okay? So for bromo, this is an example of bromothymol blue. Okay, so this solution is yellow in acidic solution, and in basic solution it turns blue. Okay, and that color change will occur over 2 pH units. Okay, so now where? Okay, so that will depend on the acid dissociation constant. It will depend on the Ka or pKa, and we will go to this a little bit down the road. So for now, we're going to leave this, and we're going to take a look at the precipitation titration. Okay. So the previous example was acid-base titration. This is the precipitation titrations. And these titrations are based on reactions that yield ionic compounds of limited solubility. Okay? So in this titration, in this example, we're titrating the solution of sodium chloride. Right? This is an electrolyte, so it is completely dissociated into ions. And we're titrating it with a silver nitrate, another electrolyte. Okay? The silver is actually one of the most widely used and one of the most important precipitating agents because it can precipitate many different ions. So in this example, we use silver ions to precipitate chloride ions as silver chloride. So this is really it forms a suspension of a very small silver chloride particles in the aqueous solution. So the solution becomes kind of milky. Okay, and it's a large family of titrations in which we use silver, and these titrations are argentometric titrations. So whenever you use silver to precipitate an ion, this is an example of argentometric titrations. And here you have the titration of Cl- with silver plus ions. Okay. Now, at the end point, this suspension turns pink. Okay. And here we also use an indicator. But that indicator actually works quite different from the indicators that are used in acid-base titration. In precipitation titrations, the indicator adsorbs at the surface of these particles, silver chloride particles. Okay? And when all chloride ions are used, this indicator turns or changes color. Okay? So it's a different mechanism, different chemistry compared to the acid base. Now, so what happens? In order to understand how these indicators work, we need to consider the electric charge of these precipitate particles that are forming in the solution. So this is an example of the silver chloride particle that is growing in the presence of excess anions or lattice anions. Lattice anions are the anions that belong in the crystal. The crystal we're talking about here is the silver chloride. So when you're adding silver ions to the solution that contains chloride, we will form these silver chloride crystals, right? But when they grow in the solution, at the beginning we have a large excess of chloride ions. Okay, and these chloride ions there will be excess of these chloride ions on the surface of the precipitate. So the surface of the particle will have a slight excess of negative charge because of these chloride ions on the surface. Okay, but as you get closer to the end point, the chloride ions will be built into the crystal, okay? And their concentration in the solution will be very, very small when you get close to the end point. Now, when you are past the end point, we will no longer have excess of chloride ions in the solution. They will be all used to build these precipitate particles. We will have now excess of the titrant, which is the silver plus ions. Okay, and these silver plus ions will be in turn adsorbed on the surface of the growing crystal particles. So the surface now, or past the endpoint, will have a slight excess of positive charge. You see the charge on this growing crystal in the solution near the endpoint or at the endpoint changes from negative to positive because the conditions in which you grow these crystals change, right? So now the indicator is itself an ion. It has a negative charge. So if the surface of the crystal, growing crystal, has a negative charge, it repels the indicator because the like charges repel, right? However, when you are at the end point, the surface will have a slight positive charge or excess of positive charge, and it will attract the anionic indicator. So it will be adsorbed. The indicator now will be adsorbed on the surface at the end point. And now the difficult part is to understand why it changes color. This is not very well understood, but the interaction between the indicator and the crystal, when the indicator is adsorbed on the surface, cause the indicator to change the color. Okay, so that's how these indicators work for the precipitation reactions. Okay, quite different compared to the acid-base reactions. The last type of volumetric titrations that I wanted to introduce are the redox titrations. So in redox titrations, the reaction obviously that we're using for this type of titrations is a reduction oxidation reaction. So one species is oxidized, the other species is reduced in this titration. And as an example here, we have a potassium permanganate, right? So KMnO4, it dissociates into the permanganate ions in the solution, which is a strong oxidizing agent. The permanganate has a very intense purple color, or dark purple color. And the reduction of the permanganate to the colorless manganese 2 plus ions in the solution will be an example of the redox titration. So the solution will turn from dark purple when the permanganate is reduced to manganese 2 plus to a faint pink at the equivalence point. Okay, so in this case, no additional indicators are necessary because the titrant is by itself an indicator. Okay, so this requires strong acidic conditions to reduce the permanganate, but when all the permanganate is used, then it is we will observe this color change. So in this particular example, we have we use this reaction in which the oxalate reacts with the permanganate. Okay, so permanganate is our titrant. We adding permanganate, and it reacts with oxalate. The permanganate is reduced. The oxalate is oxidized. When all oxalate is used up in this titration, then the added permanganate will not be reduced, will not turn clear. It will remain dark purple. So the color of the solution at the equivalence point or at the end point will have this faint pink shade. Okay, so these three types of titrations, we're going to look at these three a little bit more carefully: acid-base titrations, precipitation titrations, and the redox titrations later in the semester. Okay. All right. So there are two types of volumetric titration. So this is still a general discussion that applies to all titrations, all volumetric titrations. So in a direct titration, the titrant is added until we reach the endpoint. Okay, so analyte plus titrant will give us some products. And an example could be, for example, well, the example we can use the last one we saw, and it was the addition of permanganate to oxalic acid. The oxalic acid is our analyte, the permanganate is the titrant, and then we can determine the endpoint for this titration when the solution stays pink. That will give us the volume of the permanganate, right? So we can calculate, since this is a standard titrant, we will know the moles of permanganate once we determine the endpoint. Now, from the reaction, from the stoichiometry of the reaction, we can calculate how many moles of oxalate was used in that titration. Okay, so 2 moles of permanganate in this titration require 5 moles of oxalate. So that allows us to calculate the concentration of the oxalate. Because the amount of oxalate is chemically equivalent to the amount of oh, I'm sorry, that's a different example. So this is a simple version of a titration, a direct titration, okay? Now, sometimes, however, it is necessary to add an excess of the standard titrant, and then we determine the excess amount by back titration with a second standard titrant. Okay, so we use 2 standard reagents in a back titration. Okay, so let's try an example. The amount of peroxy disulfate, okay, S2O8 2-. Okay, the amount of this compound in a sample can be determined by adding an excess of standard oxalate. Okay, this will lead to the formation of the sulfate and sulfate ions and carbon dioxide. Okay, since we added an excess of oxalate, there will be an unreacted oxalate, C2O4, 2- in the solution remaining. And that excess has to be back titrated with a second standard reagent. For example, permanganate. Okay? So what will be the amount of oxalate in this solution? In the unknown solution, right? So the amount of oxalate will be chemically equivalent to the amount of peroxide disulfate, right? Plus the amount of permanganate used in the back titration. Okay, and then we can calculate the amount of peroxide disulfate by taking the difference between the amount of oxalate and the amount of permanganate. Okay, so we will look at an example of this in well, I'm not sure if we're gonna make it today, but let's see. Let me finish with actually this. Okay, so we need to introduce a primary standard, because in all titrations we do require a standard titrant. So this is the reagent with a known concentration. Okay, and the primary standard is a highly purified compound that serves as a reference material in titrations and in other analytical methods. Okay, so the accuracy of a titration depends critically on how accurate you know the concentration of the standard titrant. And this standard titrant is or has to be prepared from a primary standard. In order for a substance to qualify as a primary standard, it has to meet certain requirements. Okay, So it has to be of high purity. The concentration has to be accurately known for a primary standard. It has to be more than 99.9% pure. Now, it has to be stable. So atmospheric stability is important. It cannot be sensitive to light. It should also be not hygroscopic, so it should not be absorbing water from the air, because that will change its purity. Okay. The composition has to be known exactly. Now we also need to take into account some economical considerations. So it cannot be too expensive, especially if you need a lot of it, and among others, its solubility in the titration medium should be reasonable, because you don't want to spend a lot of time trying to dissolve your primary standard. Now, it should also have reasonably large molar mass. That allows us to avoid the error associated with weighing the standard and calculating the amount of moles that we have. So very few compounds actually meet this criteria. Okay, and there is only a limited number of primary standard substances that are available commercially. So as a consequence, less pure compounds must sometimes be used in place of a primary standard. The purity of the secondary standard must be established by a separate analysis. Okay, so the reagents that we need for the volumetric analysis, the standard solutions that play so important role in the titrations, ideally should be prepared using a primary standard. Okay, so this is one way of preparing the standard solutions. Okay, now these standard solutions also have to meet certain criteria that are listed at the bottom of this slide. So they should be stable. Okay, so its concentration needs to be determined only once, and then it should remain the same. The standard solution should rapidly react with the analyte. The reaction should go almost to completion, okay, in order to be useful for a titration. And you also have to consider the selectivity of this standard solution. So it needs to ideally selectively react only with the analyte, because if it reacts with something else, that's going to affect your titrations, your calculations. Okay. So one way of preparing the standard solutions is to use a primary standard. Okay, and in this case, you just weigh out the desired mass of the primary standard that contains the desired number of moles, and then you dissolve it, and you have a standard solution. Now, if primary standard is not available, we have to go through the process of titrating a standard to determine the concentration of the titrant. So if the titrant that you need to use in a titration cannot be prepared from a primary standard, you need to standardize this titrant by titrating it with a standard, with another primary standard. I know it's kind of convoluted, but for example, I mentioned several times today the titration of hydrochloric acid with sodium hydroxide, right? So one of these reagents has to be standard reagent. You need to know its concentration. So let's say you want to use the sodium hydroxide as a titrant, as a standard titrant. So you need to know its concentration, okay? But there is no primary standard to prepare the sodium hydroxide because the sodium hydroxide pellets are highly hygroscopic. They absorb a lot of moisture, and well, that basically precludes it as a primary standard because you cannot determine accurately the moles that are contained within a certain mass of that standard, right? So how do we prepare a standard NaOH? We have to titrate it with another standard. And usually for that purpose, we use the KHP, which is a potassium hydrogen phthalate. And we use it to standardize the NaOH solution. Okay? So that's the second way of preparing the standard solutions. So the titration calculations, it's nothing complicated, it's just stoichiometry. So if you have T moles of titrant, right, that are required to react with A moles of the analyte, this is just from the reaction, from the balanced reaction. Okay, so that means you can quite easily calculate the moles of titrant delivered if you know the volume. And you do know the volume because you're using the burette, right? So you can measure the volume of the titrant. So then the volume times the concentration of the titrant gives you the moles of the titrant. And then back to the reaction, right? The moles of analyte present has to be equal to the moles of the titrant multiplied by the ratio of the moles of the analyte to moles of the titrant in the reaction. The ratio of the stoichiometric coefficients from the reaction. Okay? If the reaction is 1:1, 1 mole of the titrant reacts with 1 mole of analyte, then the moles of analyte is just equal to the moles of the titrant. Okay. So now I'm going to throw at you an example, which is, let's see what happens now. Hopefully it will work. Give me a second. Should come back. Maybe not. Okay. Hold on, now the cable is too short. Huh? Okay, so let's take a look at this example. We have a sample that contains sodium chloride and potassium bromide, okay? And the sample was dissolved in water, and it required 48.40 milliliters of 0.04837 molar silver nitrate for complete titration of both halides, okay? So the precipitates that are formed in this reaction are silver chloride and silver bromide, okay? Now, this is just one titration. We have two analytes, right? Chloride and bromide. And we want to calculate the weight percent of bromide ions in the solid sample. So let's see if we can do that with this data. So let's start always in a titration, always start with a reaction. Okay. So in this case, we will have two reactions, right? The Cl minus reacts with the titrant, which is silver plus ions, and forms a precipitate silver chloride, right? Which is solid and it precipitates. Now the bromide also reacts with silver chloride and forms silver bromide solid. In both reactions, the stoichiometry is 1, okay, in both reactions. Okay, so then what we can do is we can calculate the moles of the titrant that was delivered, right? So the moles of titrant will be the volume, 48.40 milliliters, times the concentration of the titrant, 0.0837 molar, right? Okay. So this will be 2.3411 millimoles. Okay, so don't lose track of the units here because I used milliliters and I multiplied by the molarity, which is moles per liter. So somewhere along the way, we need to remember to convert the units so they are consistent. Okay. So this is millimoles of silver plus, right? So this is the titrant that reacted with the analyte. But the analyte in this case is chloride and bromide. Right? So we have one equation and unfortunately two unknowns, right? The moles of Cl minus and the moles or millimoles of Br minus. Okay, so to solve this problem, we need to express now the moles of Cl minus in terms of the mass. We want to do that because we have the mass of the sample. It's 0.2386 grams, right? And that mass contains both Cl minus and Br minus, okay? So the moles of Cl minus, right, will be equal to the moles of NaCl in the original sample, right? So that is clear. So the moles of NaCl is, I don't know it, so I'm gonna call it, the moles of NaCl will be the grams of NaCl in my sample divided by the formula weight, right? So since I don't know how much NaCl is in my sample, I'll call it X. So this is X gram of NaCl divided by the formula weight for NaCl. It's 58.433 grams per mole. Okay, and this is NaCl. Okay, so again, to be clear here, this ratio is the moles of NaCl in my sample. But the moles of NaCl is equal to the moles of Cl minus, or the moles of Na plus from the formula, right? Okay, so now what are the moles of KBr? The moles of KBr would be the mass of KBr divided by the formula weight for KBr. And the moles of KBr will be equal to the moles of Br minus. Okay? So again, I don't know the mass of KBr, so I'm going to call it Y. So I have Y grams of KBr in my sample, dividing it by the formula weight, 119.002 grams per mole. This is KBr. Okay, so I have moles of NaCl plus moles of KBr, which translates into moles of Cl minus plus moles of Br minus, right? But from my titration, I know that this, when I add up these moles of Cl minus and Br minus, I'm gonna get moles of silver plus in the titration, right? And the moles of silver plus was 2.3411 times 10 to the negative third mole, and this is silver plus. Okay, this is what we calculated. So now I converted the millimoles to moles. Okay, and so it looks like we haven't accomplished much because we still have one equation and two unknowns, right? But we have now, we know the mass of our sample. The mass of our sample was 0.2386 grams, right? And the problem says that the sample contained only NaCl and KBr. So 0.2386 has to be equal to X grams of NaCl plus Y grams of KBr, okay? Or in short, 0.2386 grams has to be equal to X plus Y, okay? So now I have two equations and two unknowns. Well, system of equations, this is chemistry class, so I'm not gonna go into details how to solve it. I'm assuming you guys can do that. So now we can calculate either X or Y, right? It's going to be, so for example, from this second equation, the X will be 0.23, let me write it down here. So the X will be 0.2386 minus Y, right? And the Y I can calculate in terms of X using the first equation. So I'll have to just solve the first equation for Y and then plug it into the this last equation I just wrote down, and that will give me hopefully the result, which is okay. So what I need is actually weight percent of bromide, right? So bromide is Y. So I would have to do it a little bit differently. I would have to take this last equation, x equals 0.2386 minus Y, and plug it into the first equation, right? And then I would have everything in terms of Y, which is grams of KBr, okay? So these calculations now should give me Y that is 0.2000 grams KBr, okay? These are all like intermediate calculations. I'm not really paying attention to significant figures here. I'm not reporting final results yet. So I have grams of KBr, right? So that needs to be translated and converted to moles of KBr. Okay, hopefully this will be clear in a second. Okay, So this gives me 1.681 millimole of KBr. Okay, I'm doing this because I need the mass of Br minus, because the weight percent of bromide ions is the mass of Br minus ions divided by the total mass of the sample. But I don't know any other way of calculating the mass of Br minus ions. I have to get, if I have the mass of KBr, I can convert it to the millimoles of KBr. Now, 1.681 millimoles of KBr, looking at the formula, tells me that I have 1.681 millimoles of Br minus, right? So now I have millimoles of Br minus. So again, using the atomic weight, I convert it into the grams of Br minus, and that would be 0.1343 grams of Br minus. Okay. So now the weight percent of Br minus is grams Br minus divided by the total mass multiplied by 100%. So I just calculated the grams of Br minus, 0.1343 grams Br minus divided by the total mass, 0.2386 grams times 100%. So that equals to 56.28% by weight of Br minus. Okay, so we did a lot of conversions here, but you can see that even this simple titration, right, if it is done correctly, can give you a great deal of information, because you can analyze these two ions that are in your in the unknown solution. Now let's take a look at an example of back titration. Okay, so in this example, we actually going to perform a Kaldal nitrogen analysis. So we're going to this is also a titration, which allows you to determine the amount of nitrogen in your sample. So we have the mass of the sample, 0.4755 grams, and that sample contains ammonium oxalate, okay, and some other material. The sample is dissolved in water and made strongly alkaline with potassium hydroxide, which converts ammonium to ammonia. Now, the liberated ammonia in this example is distilled into exactly 50 milliliters of known concentration of sulfuric acid, okay? And then the excess of H2SO4 is back titrated with the second standard reagent, sodium hydroxide, okay? So you see, this is a back titration, right? We have the first reagent is sulfuric acid. We're adding excess of sulfuric acid, okay? And then in the actual titration, we back titrate this excess of sulfuric acid that did not react with the ammonia with the second standard reagent, which is sodium hydroxide. So this is an example of back titration, okay? So there are three reactions. Okay, what do we have to calculate? The weight percent of nitrogen, okay? So there are actually three reactions that describe this whole process, right? So the first one is the ammonium oxalate reacts with potassium hydroxide, and the products are K2C2O4 plus ammonia and plus H2O. So in this first reaction, this ammonium oxalate the ammonium is converted to the ammonia. And the second reaction is where we add the excess of sulfuric acid, H2SO4, right, to make the product, which is ammonium sulfate, okay? Now, the third reaction is the actual titration reaction. So we titrate the excess of H2SO4 with sodium hydroxide, okay? So this is actual titration reaction. So the ammonia that is produced in the first reaction is converted to well, it reacts with sulfuric acid, and then the sulfuric acid, the excess of sulfuric acid, is back titrated with the sodium hydroxide. Okay. So in this example, we want to what we need to calculate is the total amount of the sulfuric acid that we used, and then subtract the excess. That will give us the amount of sulfuric acid that reacted with ammonia in the second reaction. And then we can use the stoichiometry of this reaction to calculate actually the number of moles of ammonia that was originally present. Okay? So the total H2SO4, we added 50 milliliters of 0.5035 molar H2SO4, right? So we had initially or originally 2.5175, and this is again millimoles of H2SO4, okay? So this is the total H2SO4, okay? All right, so now in the back titration, we used 11.13 milliliters of NaOH, right? If we multiply it by the concentration of NaOH, which is 0.1214. It's sometimes more convenient to use the milliliters and millimoles. So if it is molarity. Molarity is moles per liter or millimoles per milliliter. You're gonna get the same numerical value, okay? So this is millimoles per milliliter. So these are the moles or millimoles actually of sodium hydroxide that were required to reach the end point in the back titration. Okay, so I'm looking now at the third reaction. Okay, and the stoichiometry of this reaction is we need 1 millimole of H2SO4 per 2 millimoles of NH3. Okay. So now I'm converting the millimoles of NaOH to millimoles of H2SO4. Okay. Using my titration reaction. So this is the excess of H2SO4, 0.6756 millimoles of H2SO4 in the back titration. So this is the unreacted H2SO4. Okay, so this is in back titration. So this is unreacted H2SO4. So the moles of, okay, so the moles or millimoles, okay, millimoles of H2SO4 that reacted with ammonia with NH3 will be the total H2SO4, which was 2.5175 minus the unreacted H2SO4, 0.6756. Okay, so this is 1.8419 millimoles. So this is 1 point. 1.8419 millimoles of H2SO4 reacted with ammonia. But we need 2 moles of NH3 per 1 mole of H2SO4. Okay, because now the quantity that we need to calculate here is the weight percent of nitrogen. Okay, so we have 1.8 of H2SO4, right? And we need 2 millimoles of NH3 per 1 millimole of H2SO4. Okay, so the moles of NH3 will be 3.6838 millimoles of NH3. Okay. Now, 1 millimole of NH3 has 1 millimole of nitrogen, right? That's just from the formula. There's 1 mole of nitrogen atoms in 1 mole of NH3 molecules, okay? So I have 3.6838 millimoles of nitrogen, okay? So now everything is quite straightforward from here, right? Multiplying the millimoles of nitrogen by the atomic weight will give you the mass of nitrogen. Okay, so that mass of the nitrogen will be 0.05160 grams of nitrogen. Okay, and then so this is not really equals here, and then the mass of the nitrogen divided by the mass of the sample will give us the weight percent of nitrogen in the sample. Okay, so 0.05160 grams of nitrogen divided by 0.4755 grams, that's the mass of the sample, and multiplied by 100% will give us 10.85% of the nitrogen in the sample. Okay. So these calculations can be quite involved sometimes in the titrations, but if you keep track of the chemistry and units and all these conversions, that shouldn't be too difficult. The best way is to practice, okay? So if you open the textbook at the end of the chapter 6, there will be quite few examples that you can try. I will be posting another problem set soon and another homework probably tomorrow. So use all that to practice. Okay. So now that's the calculations. Okay. Now we need to talk a little bit about the. This is the same example. Now we need to talk a little bit about the equilibrium of slightly soluble salts, because this is something we need to take into account when we performing or carrying out precipitation titrations. Okay, so in precipitation reactions, so these are the reactions that are used with the precipitation titrations, right? The solid precipitate is formed, okay? And for a reaction to be useful for a titration, the solid that is formed must have very low solubility, and it must stay in the solution as solid, okay? However, we know that all solids will dissociate into ions to some degree. Some solid will dissociate to a larger degree, some solid will dissociate only slightly in the solutions. So in order to calculate or to get that solubility, we need to look at the solubility equilibria. And these solubility equilibria are normally treated as a dissociation reactions. So for a, okay, where is my dissociation reaction? There it is. So for a sparingly soluble salt, right, like this one, okay, in a saturated solution, it will dissociate into ions. So here is an example of lead iodide. It dissociates into lead 2+ and iodide ions. And the equilibrium constant for this reaction is called the solubility product. Okay, because the reactant is solid, so it does not appear in the equilibrium expression. So we have only the concentrations of the ions in this expression. So in a saturated solution, the ions are in equilibrium with the solid, and the product of their concentrations has a constant value. So that's the equilibrium constant, which is called a solubility product for these dissociation reactions. Now, but keep in mind that this is not a static picture, right? The equilibrium is a dynamic state. So the ions from the solid are entering the solution, and at the same time, the dissolved ions are recrystallizing. but the rates of the forward and reverse reactions are the same. So it appears as the concentrations are constant. That's what we consider the equilibrium, right? So we need to determine the solubility, and in order to determine the solubility, we can use the equilibrium constant. If, on the other hand, you know the solubility and you want to, you can calculate the equilibrium constant. The solubility is defined as the maximum amount of the solute that can be dissolved in a solvent at the equilibrium. Okay, so this is the solubility. So the solubility of this lead iodide is the concentration of Pb2 plus ions, right? This is the amount, because the concentration of Pb2 plus at equilibrium tells you how much of the solid PBI dissolved, because this Pb2 plus comes from the PBI2, okay? And the concentration of Pb2 plus at equilibrium can be calculated from the solubility product. So that's how we can go back and forth between these. All right, so in the title of this slide, I mentioned slightly soluble salts, okay? Because solubility of salts is sometimes somewhat loosely defined in terms of the volume of solvent needed to dissolve 1 gram of solute. Okay, and then based on that amount of the solvent that is needed to dissolve 1 gram of the solute, we define the salts as very soluble if less than 1 milliliter of the solvent is needed to dissolve 1 gram of the sample, all the way to practically insoluble solids. And these are the solids that require volume of the solvent in excess of 10,000 milliliters in order to dissolve 1 gram of the solvent, of the solute. Okay, so for our precipitation reactions, we need to form the solid, and the precipitate has to stay as solid. So for us, for our purpose, the slightly soluble salts will work. So these are the salts, according to this definition at least, that require something between 100 and 1,000 milliliters of the solvent to dissolve 1 gram of the salt. Okay, so if that is the volume of the solvent required to dissolve 1 gram of the solid, this solid would be called slightly soluble. Okay, and that corresponds to 1 gram per 100 milliliter, or all the way to 0.1 gram per 100 milliliters. So either way, all solids that dissociate into ions will exhibit some limit to their solubilities. Okay. Now, the solids whose saturated solution exceed the concentration of about 0.01 moles of ions per liter, well, that's where we get into a little bit of a problem, because these solids, they cannot be treated by the simple equilibrium constant. And this is because of the formation of ion pairs. Okay, so if the concentrations of these ions is too high in the solution, they will start forming ion pairs. So this is the two ions attracted by the electrostatic forces, basically, but they stay in the solution as one unit. It's not solid, it's just the two ions staying together in the solution. But they are, because they are together, well, they affect the concentration of the individual ions. So this is mainly the reason why we are going to be limited to the salts that fall into this category of sparingly soluble salts, because they dissociate into ions to a very small degree in the solution, and the concentrations of these ions will be very low, very small. Okay, so this way we avoid all these problems related to the formation of ion pairs. Okay. Okay. So so now going a little bit farther with these reactions that are useful for precipitation titrations will be the reactions in which the analyte, or the ion that we want to determine concentration, is precipitated and insoluble precipitate is formed. Okay, so for example, let's assume that you want to precipitate iodide ion. Okay, so that iodide ion which is in the solution, okay, comes from the potassium iodide. So we have potassium iodide, and we want to determine the concentration of iodide. So we may try to precipitate it, right, in some suitable reaction. For example, we can try adding lead nitrate. So we basically mixing two electrolyte solutions, Ki, which is the source of iodide, and PbNO3. So this is the lead iodide. Okay. So now the precipitate may form or may not form, right? That will depend primarily on two factors. The first is, well, we need to determine all the possible combinations of ions that could result when the two solutions are combined, and then we can check the solubility tables in order to determine which of the solid is insoluble. So which of the solid would have very little or very small solubility. Okay. So in this particular example, the solids that can be formed is PbI2, right? That's one solid, and the other solid is potassium nitrate, KNO3. Okay, and then so once we determine the possible combinations, then we would go to the solubility tables or the solubility products, the equilibrium constant, that would also do. And what you would find is that the solubility of PbI2 is very small. The potassium nitrate is very soluble. It's another electrolyte, right? So that would not be of any use for us. But PbI2 has a very low solubility. And you can see that because when you mix, if you were to mix these two solutions, you would immediately see the yellow precipitate forming in the solution. So that's potassium iodide, the solid, okay? But there is, so that's just one thing, the one factor. The other factor is the concentration of these ions. In order for the precipitate to form, right, the concentrations of the ions have to be great enough so that the reaction quotient, right, exceeds the KSP value. Okay, so the precipitate will only form if the concentrations of the ions, the product of the concentrations of the ions, will exceed the KSP. So then it will start forming the precipitate until the product of the concentrations is equal to the KSP, and the equilibrium is reached. Okay, so these two things: the solubility of the possible solid that can be formed when you mix the solutions, and then the concentrations of the ions. Now the solubility, unfortunately, does not tell the entire story of solubility, and that is because of these ion pairs. Okay, so there are, of course, complications that may arise from other reactions, right? Because if some of these ions react with something else, okay, that is something we would have to take into account. But most salts form soluble ion pairs to some extent. Okay, so the ion pairs will always be formed in the solution. However, if the concentrations of the ions are very, very small, these concentrations of the ion pairs will be also small, and it will not affect our measurements. So, to give you an example, the calcium sulfate, right? In a saturated solution of calcium sulfate, about 2/3 of the dissolved calcium is calcium 2 plus ions, okay? And 1/3 exists as an ion pair, calcium sulfate. So this is not a solid, this is just two ions held together by electrostatic force. But this 1/3 of calcium ions does not function as individual ions. They are paired with the sulfate. So the concentration of calcium ions that you would calculate from the simple dissolution equilibrium, right, would be quite different from the actual concentration of calcium ions in the solution because of the formation of these ion pairs. Okay, so for this particular example, right, if these two ions, Pb2 plus and iodide, if only these two ions reacted to form the solid Pbi2, right, the solubility of Pb2 plus would always be very low if there was an excess of iodide ions. And we can tell that based on the numerical value of the solubility product. It's very, very low. It's very, very small. So the concentrations of Pb2 plus and iodide ions in a saturated solution must also be small because they have to obey this equilibrium, right? However, we actually observe experimentally that when the concentrations of iodide are a little bit higher, on the higher side, that causes this more Pbi2 solid to dissolve. So the solubility actually depends or changes depending on the concentration of these I- ions. And we explain this by the formation of a complex ions. So the species here, for example, in the reaction 3, this is an ion pair, Pbi2, and we indicate it by the AQ in the parentheses. So aqueous ion pair. So so this is the dissolved Pbi2, but it contains two iodine atoms bound to just one lead atom. So this is not a solid. And this reaction, the reaction number 3, is not the reverse of the reaction number number 1, because in reaction number 1 we have solid PbI2. In reaction number 3 we have ion pair. Okay? So experimentally, what we see is that at low iodide concentrations, the solubility of lead iodide is governed by the precipitation of PbI2 as a solid. But at high concentrations of I minus, all these reactions from 2 through 5, okay, all these reactions are driven to the right. The Le Chatelier principle at work here. And the total concentration of dissolved lead is considerably greater than the concentration of PbI2, Pb2 plus that you would calculate from the first equilibrium, from the dissolution of PbI2. Okay? So that is a little bit of a problem in our calculations, and we have to be aware of that. However, we are going to assume in what follows that we don't have to explicitly deal with this ion pairing. Okay, and we will only assume the first equilibrium. Okay, but in order to give you an example and also to clarify how important this and how useful these equilibria are. Okay, so consider this. All these equilibria, okay, they have to be satisfied simultaneously. Okay, so if you know the concentration of I minus iodide ions, we can calculate the concentration of Pb2 plus ions, because the first equilibrium has to be obeyed. Okay, no matter what are the other reactions that might be happening in the solution. Okay, so we can use this first equilibrium. If you know the concentration of I minus, we can plug it into the solubility product for PbI2 and get the concentration of Pb2 plus. Okay, so and this is regardless of whether there are other reactions involving Pb2 plus. This equilibrium has to be satisfied. So now the concentration of Pb2 plus that satisfies the first equilibrium, okay, the top reactions, it must satisfy all the equilibria in which we see Pb2 plus concentration, okay? Because in your solution, there can be only one concentration of Pb2 plus, okay? We cannot have different concentrations of Pb2 plus when you look at these different reactions. Okay, so that's out of the way. Maybe for a little bit too long, but I wanted to make you aware of this ion pairing. So let's finish this with this example. Okay, so we have a solution that is saturated with PbI2. So this is a solution at equilibrium, and that solution contains dissolved I minus, but somehow we were able to calculate or measure the concentration of I minus. And that concentration was 0.001 molar, okay? So now let's find the concentrations of PBI plus, PBI2, the ion pairs, PBI3 minus, and PBI4, 2 minus. Okay? So for this, okay, I don't have the reactions here. Okay, so PBI plus, okay? So PBI plus is formed when PB2 plus reacts with iodide. The possible product is PBI plus, okay? The equilibrium constant for this reaction, so let me call it K1, is the concentration of PBI plus, okay? Okay. Divided by the concentration of PB2 plus times the concentration of I minus. And its numerical value is 1.0 times 10 to the second. Okay. So we have K1. We do know the concentration of I minus. It's 0.001. Okay. But in order to calculate the concentration of PB1 plus, we need K1, right? We also need concentration of PB2 plus, okay? So, but this is a saturated solution of PBI2. So in that solution, the dissociation of the solid PBI2, right, leads to the formation of PB2 plus and 2I minus, okay? The solubility product for this solid is the concentration of PB2 plus, right, times the concentration of I minus squared. And it is equal to 7.9 times 10 to the 9th power. Okay? So from that last expression, we can calculate the concentration of PB2 plus. It's going to be KSP divided by the I minus squared. KSP is 7.9 times 10 to the 9th power. The I minus is 0.01 squared. Okay, so the concentration of PB2 plus is going to be 7.9 times 10 to the negative third molar. Okay, so we just use another equilibrium to get the concentration of PB2 plus. Now, all we have to do is plug it into here because this is PB2 plus. Its concentration in the solution has to be the same, no matter which equilibrium you are looking at. Okay, so the concentration of PBI plus will be equal to the K1 is 1.0 times 10 to the second power times the concentration of PB2 plus that we just calculated, 7.9 times 10 to the negative third, times the concentration of I minus. 0.001. Okay. Thank you. 0.001. Also, I have a typo here as well. Okay. All right, so this concentration will be, should be 7.9 times 10 to the negative fourth molar. Okay? So we're just playing with the equilibria. Okay? So now, if you want to calculate the concentration of ion pair, PbI2, okay, you would use this equilibrium, right? This equilibrium. And the PbI2 concentration would be the equilibrium constant times the concentration of Pb2 plus times concentration of I minus squared. Okay, so once you calculate the concentration of Pb2 plus using this equilibrium, then you can calculate the concentrations of all these other complex ions using the other equilibria. Okay, so you can see that this treatment is quite complicated, and very soon I'm going to complicate it even more by introducing activity. Okay, but for now let's stop here. Okay, so solubility products. Okay, solubility products we're gonna use to calculate the solubility. Now, to finish this discussion about the equilibria of slightly soluble salts, we just have to take a look at two more things that are actually important because they can affect the position of the equilibrium, which means that they can affect the solubility of the of this slightly soluble salt. Okay, so we can either dissolve more salt or we can dissolve less salt. Okay, so these two factors that affect the solubility are the pH of the solution and a common ion effect. Okay, so let's start with the pH. So dissolution of calcium carbonate, according to this particular reaction, produces calcium and carbonate ions. Okay. Now, when you add acid, okay, to the saturated solution of calcium carbonate, the carbonate ion can react with the acid, with H plus ions, okay? And it will make bicarbonate, okay? Bicarbonate can react with another H plus to create carbonic acid, okay? So what we're doing here by adding acid, we removing the product, the carbonate, okay? So now again, invoking the Le Chatelier principle, if you're removing product from your reaction, the equilibrium position will be shifted to the right, which means more calcium carbonate will dissolve, right? So adding acid or adding H plus, which is equivalent to lowering the pH of the solution, increases the salt's solubility, but only if the anion of the ionic solid is that of a weak acid. Okay, so the carbonate has to react with the H plus. Carbonate is the anion of a weak acid, the carbonic acid. Okay, there is a little bit more to this reaction. Well, carbonic acid is actually produced when dissolved carbon dioxide combines with water. Okay, so okay, where is the reaction? So that means the relative concentration of the carbonic acid is really the concentration of CO2 dissolved in water in equilibrium with the water. So that means, or with carbonic acid. So that means if you make more carbonic acid by adding by decreasing the pH of the solution, where the first effect is that the solubility of calcium carbonate will increase. Okay, but because we're making carbonic acid and it's in a saturated solution, it has to be in equilibrium with CO2. If you make more carbonic acid, it also means that you will have more CO2, and that CO2 is actually now released from the solution, and that's why the solution is fizzling. Okay, so this is a test for carbonate, actually. A very simple test. You can add acid to the solution, and if there is a CO2 bubbling out of your solution, it means that you have carbonate in there. Okay, so that's one thing. Increasing the concentration of H+ increases the compound's solubility if the anion of the compound is that of the weak acid. Okay, so that's one thing. Do we have time? Or we do maybe have time to finish with this common ion effect. Now, the common ion effect is also going to affect the solubility, but in the other direction. So if you add a common ion to a saturated solution, it will lower the solubility of the ionic compound, and you will see more precipitate in the solution. Okay, so if you have lead chromate, the solution of lead chromate. Okay, this is a slightly soluble salt, and in saturated solution, the precipitate has this nice yellow color. So this is the dissolution reaction right here. Okay, so now if you add chromate to this solution, for example, if you add sodium chromate to this solution, what you should see is that all of a sudden more precipitate forms in this solution. Okay, and the reason for that is we adding product, right? The chromate. We increasing the concentration of chromate. So invoking Le Chatelier principle again, adding product shifts the equilibrium to the left, right? Because the system is trying to oppose the change that you are imposing. The change that you are imposing is the increasing the concentration of chromate, Cr042-. So the system will try to go in a direction that decreases this concentration. And that direction is to form more solid lead chromate. Okay, so that's why you see there's more solid forms in this solution if you add common ion. Okay, so that is the common ion effect. Okay, I believe we can finish this and then I'll stop. So this is again going back to the actually to the beginning almost, because if you want to write down the expression for the equilibrium constant for the reaction in which a solid salt or an ionic compound dissolves to give ions in the solution, we can do that actually even without looking at the reaction. All we need is just the formula for the salt, right? So if you have the formula of the salt, so we have the cation M and we have m moles or molecules, atoms of the cation in the formula, and x is the anion, right? And small x is the number of moles in the formula. Then from the stoichiometry, we know that the solubility product or the equilibrium constant expression will be the concentrations of these ions, cation and anion, with the exponents that correspond to the stoichiometric coefficients in the formula. Okay, so the point of this is that if you look at the formula for magnesium carbonate, right, you can, just by looking at this formula, you can immediately write down the solubility product, and it's going to be the concentration of magnesium 2 plus times the concentration of carbonate. Okay. If you look at the second compound here, iron hydroxide, the solubility product is the concentration of iron 2 plus ions times the concentration of hydroxide squared, right? Because there are 2 hydroxide ions in the formula. Okay, and the last one is calcium phosphate. So the solubility product is the concentration of calcium 2 plus cubed to the power of 3, and the phosphate concentration squared. Okay, because of the coefficients in the formula. Okay, so that is something we should be able to write down very quickly without really writing down the whole reactions. Okay, so that's just one thing. Okay, can we do this one more example? That's going to be quick, but this will allow us to calculate. So in this example, we're calculating the solubility product, the KSP, from the solubility. So we know the solubility of lead sulfate. Okay, it's 4.25 times 10 to the negative third grams per 100 milliliter. We want to calculate the KSP. Okay, so since the salt in question is lead sulfate, PbSO4, which dissociates into Pb2 plus and SO4 2 minus. Okay, the KSP is concentration of Pb2 plus times the concentration of SO4 2 minus. Okay, so so from this reaction, we know that the concentrations of Pb2 plus and SO4 2 minus in saturated solutions should be the same, right? They should be equal. And we know the solubility of the solid PbSO4. It's 4.25 times 10 to the negative third. That solubility is the concentration of Pb2 plus that we need to calculate. Although for the equilibrium constant, we need the molarity. We are given this concentration in grams per 100 milliliters. So this is 4.25 times 10 to the negative third grams per 100 milliliter of the solution. Okay. So I need to convert it to molarity. Okay. So I need to convert it to liters. Okay, so 1 liter is 1000 milliliters. Okay, so these units will cancel. I'll have liters, and then I need to divide the mass by the molecular weight in order to get the moles of Pb2 plus. Okay, so this will be so this will be moles PbSO4, because this is solubility, and the molecular weight is 300.3 grams PbSO4. Okay, and 4.25 times 10 to the negative 3, that's grams PbSO4. So when you calculate this, you will get the moles per liter, which will be the concentration, right, in the molarity. So that's 1.40 times 10 to the negative 4. And this is the molarity. And this is the solubility. Okay, so this is the concentration of Pb2 plus. And it's equal, based on the reaction, right? It's equal to the concentration of SO4 2 minus. So this is, because it's molarity, it's called molar solubility. So now, once we have this, it's Pb2 plus times SO4 2 minus. So that's going to be 1.40 times 10 to the negative 4 squared. So it's 1.96 times 10 to the negative 8. You can do these calculations in the opposite direction, right? You can calculate the molar solubility if you know the KSP. So we have calcium hydroxide, which is a solid, okay? And it dissociates into calcium 2 plus and OH minus ions in the solution. Okay, so the KSP for this reaction, the equilibrium constant for this reaction is 6.5 times 10 to the negative 6. So what we do need to calculate is the solubility. So in this case, the solubility of calcium hydroxide will be the concentration of calcium 2 plus ions at equilibrium. Right? That's how much this concentration of calcium 2 plus ions tells us how much of calcium hydroxide dissolves when the system is in equilibrium. So to do that, the easiest way to keep track of this is to use the concentration tables, right? So we have the initial concentration, okay? So initial concentrations, okay? And for calcium hydroxide, this is a solid, okay? So it will not be present in the equilibrium constant expression, okay? Now, initially, the concentrations of calcium 2 plus and OH minus are 0, right? At equilibrium, the final concentrations, well, the calcium hydroxide is still a solid, does not change, but the calcium 2 plus concentration will be unknown because some of the calcium hydroxide will dissolve, right? So I'm going to call it X, right? And according to this reaction, the concentration of OH minus ions has to be twice that of the concentration of calcium 2 plus, so 2X, right? So the KSP, or the equilibrium constant for this reaction, is the concentration of calcium 2 plus, right, times the concentration of OH minus squared. And it is equal to 6.5 times 10 to the negative 6. So 6.5 times 10 to the negative 6 equals the concentration of calcium 2 plus is X, times 2x squared, right? So this is a simple equation to solve, although we have x to the power of 3, but we can quite easily solve it for x. And the x from this equation will be equal to this. This is KSP, 6.5 times 10 to the negative 6 divided by 4, right? So this concentration will be 1.2 times 10 to the negative 2. And this is in moles per liter. So this is a molar solubility. This is what we have calculated. Okay? So only 1.2 times 10 to the negative 2 moles of calcium 2 plus ions per liter of the solution will be present at equilibrium. We expected this to be small because the KSP is quite small. It's 10 to the negative 6. Okay? So this is nothing much than that. Okay, so now the second case. Now we dissolving the same compound, calcium hydroxide, not in water, but in 0.1 molar solution of calcium nitrate, right? So let's do the same concentration table. So calcium hydroxide solid dissociates into calcium 2 plus 2OH minus. Okay, so the initial concentration, this is solid, right? But this time we have solution of calcium nitrate. This is an electrolyte solution, so initially the concentration of calcium 2 plus will be 0.1, not 0, right? So it's going to be 0.1. This will be 0. And at equilibrium, so the final concentration, this is still solid. Now at equilibrium, some calcium hydroxide will dissolve. The concentration of calcium 2 plus from dissolution of calcium hydroxide will be X, right? But I have to add the 0.1 that is initially in this solution from the calcium nitrate. So plus 0.1. And the concentration of OH minus will be 2X. Okay? So I have the same KSP, calcium 2 plus concentration times OH minus concentration squared. Okay, so now what I have to solve, however, is KSP equals 0.1 plus X times 2X squared. Okay, and that equals this equilibrium, although there are other sources of calcium 2 plus, like the nitrate, but the concentration, there's only one concentration of calcium 2 plus in this solution. So this equilibrium has to be obeyed or satisfied. And the KSP is constant, and it's going to be still 6.5 times 10 to the negative 6. However, now solving this equation proves to be a little bit more difficult, right? Because we have this additional term, 0.1 plus X. So what chemists usually do, they use an approximation to solve it, okay? This approximation is justified because if you compare X to 0.1, you actually expect X to be much smaller than 0.1. Okay. Okay. So let's just assume that this is true. If this is true, we can drop X from the term in parentheses. Okay. And our equation becomes 0.1 times 2x squared equals 6.5 times 10 to the negative 6. Okay? So this is now very simple equation to solve. If you solve it for x, it will be now the square root of 6.5 times 10 to the negative 6 divided by 4 times 0.1. Okay, and x will be correspondingly 4.0 times 10 to the negative 3. Okay, and this is in moles per liter, so this is still molar solubility. Okay, so now before we start comparing this solubility to the solubility of calcium hydroxide in water, let's first justify our approximation. When can you use it? Okay, so normally we use this 5% rule. So we compare the value of x, okay, which is, okay, the value of x is 4.0 times 10 to the negative third. We compare it to the 0.1, okay? So divided by 0.1 and you multiply it by 100%. So this will be equal to 4%, okay? So that tells me that the value of x is only 4% of the 0.1. And as long as the value of x is less than 5% of 0.1, this approximation is justified. You will not introduce a large error in calculating x, okay? Now, why 5%? Oh, well, that's much more difficult to explain. But usually, the values of KSP that are listed in these tables, they are not accurate. Their accuracy is also in the range of 5%. Okay, so by using this approximation, we actually introduce another error which is comparable to the uncertainty in KSP. That would be one way of explaining this. Okay, so 4% is below 5%, so this approximation is justified. Okay, this is actually consistent with what they tell you in the general chemistry about this 5% rule. Okay. There are other like rule of thumbs that you could use, but this one is quite straightforward. Okay. All right. So now let's compare the molar solubility of calcium hydroxide in water, right? 1.2 times 10 to the negative 2 to molar solubility in calcium nitrate, 4.0 times 10 to the negative 3. So clearly, the solubility is much smaller in calcium nitrate solution, right? Because now you can explain it, it's a common ion effect, right? We have the common ion copper 2 plus present in the solution, and it lowers the solubility of the solid. You can invoke the Le Chatelier principle, adding the common ion, calcium 2 plus, which is the product, will shift the equilibrium to the left. So we will produce more solid, which means it will be less soluble. Okay, less of the calcium hydroxide will be dissolved at equilibrium when the copper 2 plus from another source is present. Okay, and that increase is not small. Okay, so if you calculate the percent change, right, which is the solubility in calcium nitrate, 4.0 times 10 to the negative 3, minus the solubility in water, 1.2 times 10 to the second power, and divided by the solubility of calcium nitrate, again, 4.0 times 10 to the negative 3, multiplied by 100%. So that's how we calculate the percent change. You will see that the percent change is about 66.6%. Well, that's negative, right? It decreases. So that's the percent change. It's quite significant change. So if you're doing your calculations, you might want to account for these common ions. Okay, so that was the example that shows how the common ion actually can affect the solubility of the solid. All right. So now let's take a look at a simple precipitation titration. Okay. So we are going to consider the titration of 23.76 milliliters of solution of iodide. The concentration of iodide is 0.0845, and we're titrating this solution with silver ions. The concentration of silver ions is 0.0845 moles per liter. Okay? So this is an example of argentometric titration because we're using silver plus ions. The source of silver plus ions can be, for example, silver nitrate, right? And that will give us the silver plus ions in the solution. Okay. Now we need to somehow design how to detect the endpoint in this titration, because you will keep adding silver plus ions to the solution of containing the iodide until the equivalence point, right? Equivalence point is theoretical, that can be calculated based on the reaction, but in the actual titration, you will determine the endpoint. Okay. Now, one of the possibilities here is to use a silver electrode, and we can measure the potential of that electrode during the titration. This electrode is sensitive. The potential will respond to the changes in concentration of silver plus ions. So by measuring the potential, we will be able to detect changes in the concentration of silver plus ions. Okay. So now let's start by trying to calculate the volume of, so this is the setup for this titration, right? Okay, so we have a burette with the titrant, silver nitrate, and then the solution in a beaker with the that contains the analyte, iodide ions. Okay. Now, in this example, we do know the concentration of the iodide, okay? But normally, this is something you don't know, and you performing this titration to calculate the concentration of iodide. But for our purpose, we will assume that we know this concentration because we want to calculate the equivalence volume, okay? All right, so we will start with calculations of the volume of silver plus titrant solution that is needed to reach the equivalence point. So at the equivalence point, the amount of silver plus ions and iodide ions will be chemically equivalent. All right? And then we can try to discuss the titration curve that we would observe. Okay? All right, so the titration curve that we would get performing this titration would be like that. Okay, this is a sigmoidal titration curve. compared to these other titration curves that we have seen before or not. Okay, so this is basically the electrode potential on the y-axis and the volume of the titrant on the x-axis. Okay, so so let's calculate first. We were supposed to calculate the equivalence volume. So at the equivalence point, right? If we recall the titration, the silver plus ions react with iodide, and the product is silver iodide precipitate. Okay, so this is a 1-to-1 titration, and at the equivalence point, we will add just enough silver plus ions for a complete reaction with all the iodide ions that are present in the solution. Okay, so at the equivalence point, the moles of silver plus ions and iodide ions will be equal, right? Should be the same. So that means the concentration of the iodide was 0.0845 molar. So this is concentration of I minus times the volume of this solution from the problem. This is something we do know. It's 23.76 milliliters. So times 10 to the negative third if I want to convert it to liters. So these many moles of iodide is present in the solution, that is in the beaker. And I'm titrating this solution with the silver plus titrant. So at the equivalence point, the moles of the silver plus ions have to be equal. Since the concentration of silver plus, the titrant is the same, 0.0845, right? So this is the concentration of the titrant, okay? The volume that contains this number of moles that is the same as the number of moles of iodide is VEQ. So that's the equivalence volume. So at that volume, I'll have same number of moles. So we can calculate it to be, this is Q, equivalence, right? So this is 23.76 milliliters, okay? So that titration curve that you see here, right, was obtained by adding small increments of the titrant, silver plus, and measuring the electrode potential. Okay, so this is electrochemistry. That's the second part of this course. We will talk about it, but for now, we just have the signal, which is the electrode potential versus the volume of the titrant. So what can we see, or what can we tell from this titration curve? Okay, so if we follow the course of this titration with a silver electrode that again responds to the concentration of silver plus ion, we see that a relative constant voltage until we get close to the equivalence point. So at the beginning of this titration here, the voltage is relatively constant, right? Around 650 millivolts, until we get close to the equivalence point. So at the equivalence point, okay, essentially, so this is here. So at the equivalence point, essentially all iodide is used up in this titration, okay? And the concentration of silver plus ions will dramatically change because we keep adding silver plus. That's our titrant. So now it does not, so prior to the equivalence point, okay, all added silver plus ions react with the iodide to form the precipitate, silver iodide, right? So the concentration prior to the equivalence point, the concentration of silver plus in the solution is very low and nearly constant because we immediately use all that silver plus added. Okay? But when iodide has been consumed, the concentration of silver plus ions will suddenly increase because, again, we keep adding the titrant, right? And it's no longer consumed by I minus. So this change in the concentration of silver plus ions at the equivalence point will cause the abrupt change in the potential of the silver electrode. And this allows us to determine the endpoint. Okay? So this, if you didn't know the equivalence volume, right? If you didn't know the concentration of the iodide, you would still get this titration curve. Okay? From this titration curve, the middle part of this vertical section is taken as the endpoint in the titration. Okay? So you can see that it is indeed very close to the theoretical equivalence volume, which is 23.76. So from that scale, you can estimate it, but it should be very, very close to the equivalence volume. Okay? So we would have, so from the titration, we would have the endpoint, which is the volume of the silver plus. So this is a titrant. We know its concentration. We can calculate the moles of silver plus, right? Once you know the moles of silver plus, you look at the titration reaction, and you can, from the stoichiometry, you can determine the moles of the iodide or the analyte. So that gives you the moles of the analyte. You have the volume of the solution with the analyte, so you can calculate its concentration. Okay. So that would be the case. So this tells us the relative concentration, right? At the beginning, before the equivalence point, all silver plus is consumed, and the concentration is low and pretty much constant. Okay. Now at the equivalence point, okay, I cannot erase it. At the equivalence point, all I minus is consumed. So the concentrations of iodide and silver plus have to satisfy the solubility product. So they will be equal and quite small, again, both of them. And then when you keep adding the titrant, the concentration of silver plus will become greater and greater. That will change the electrode potential, but at some point it will become saturated, so the bottom part of this titration curve will also kind of flatten. Okay, so these are the relative concentration. Okay, so that is the precipitation titration. Okay, and here we precipitated just one ion. Okay, but what if you have two ions in the solution? Okay, so let's say you have not only iodide in your solution, but you have also chloride, Cl- ions. Okay, so we can use the same setup for this titration, right? And we can use the same electrode to monitor the concentration of silver plus ions. So when you run this titration, now you will get two endpoints. One corresponding to the precipitation of silver iodide, and the second one corresponding to the precipitation of silver chloride. So there are two questions here, okay? Which precipitate will form first? So in other words, whether will it be iodide that is precipitated first, or will it be chloride that is precipitated first? Okay, so this is relatively easy to answer that question. The less soluble precipitate will form first. Okay, so in this case, you look at the solubility product for silver iodide, it's 10 to the negative 17th. Okay, so it's much lower than the solubility product for silver chloride. It's 10 to the negative 10th. So the difference is 7 orders of magnitude. So silver iodide will be precipitated first because it's less soluble, and then we will have the second endpoint for the chloride. So these are the sections of the titration curve that allows us to calculate the volume of the titrant at each endpoint. Okay, so the first endpoint, this one, right? It will occur when all iodide is consumed, right? And the second endpoint will occur when all chloride is used up. Okay. So now, prior to the first equivalence point, right? Again, we will have very low concentration of silver plus that is governed by the solubility of silver iodide. Okay. This silver iodide, it is a little bit of the solid will redissolve. Okay, but its KSP is very, very small, so that will be very, very small amount. Okay, and if you recall, the precipitate is formed when the Q, the reaction quotient, right, when it exceeds the KSP, the equilibrium constant. Okay, so that will first happen for the silver iodide because its KSP is much, much smaller than the solubility of silver chloride. Now, so between the first and the second equivalence point, so in this region, okay, in this region, all iodide is precipitated, okay? All iodide is precipitated, and chloride ions now are being consumed by in the reaction with silver plus ions, and the silver chloride is being precipitated. But the solubility of silver chloride is greater than that of silver iodide. So it will be precipitated later. Now, after the second equivalence point, right, the concentration of silver plus will increase because now it's not consumed in the reaction with iodide or Cl minus. They are all precipitated. So the electrode potential of the silver electrode in this experiment will be will change again abruptly, giving us the second endpoint. Okay, so now if you have this titration curve, the first endpoint to determine the volume at the first endpoint, you take the middle, I'm sorry, not the middle part of the, not the middle of the steep section, okay? For the first endpoint, this inset actually shows how to estimate the volume at the endpoint. Okay, so we need to extend this vertical line and extend this horizontal line and read the volume when these two lines cross. So that's this point. So that will be the iodide endpoint. The reason for that is because the silver chloride actually starts precipitate before all silver iodide is precipitated. So this reading the endpoint in this way introduces a smaller error compared to if you took the middle part of this steep section. Okay. The second endpoint, we just use the middle part. Okay. But for the first endpoint, we need to do a little bit more a more careful estimation of the endpoint. Okay. So then, one more thing. I'm not sure if is this here. Okay. I will skip this part. I will give you this on the blackboard. This example shows how to calculate the concentration of iodide and the concentration of the chloride ions. The only thing that you need to keep in mind here is once you determine the endpoints, right, using these methods that we just discussed here, to precipitate the first ion, the iodide, okay, we used 23.85 milliliters of the titrant, okay? So now if you know the concentration of the titrant, you can calculate the moles of the titrant and then the moles of the analyte, the iodide, okay? Now, for the second ion, for the chloride, what is the volume of the titrant solution that was actually used to precipitate the chloride ions? That will be the difference between the second endpoint and the first endpoint, okay? The second endpoint is at 47.41 milliliters of the titrant. But that's the total volume. This volume was used to precipitate iodide and chloride. If you want to know how much titrant was used to precipitate chloride, you have to subtract the first endpoint, 23.85, from 47.41, because 23.85 milliliters of the titrant was used to precipitate iodide. And now we're calculating chloride. Okay, so that's the only thing to keep in mind when you're doing these calculations. Okay, but that would take us quite a bit of time, so you can try. I'll give you the solution on the blackboard to this, but please do try, and the problem, please do try to solve it. Okay, calculate the concentrations. Now, there are two general types of the precipitation titrations, the Volhard and Fayence titrations. Okay, this table shows you what kind of ions you can analyze using these titrations. The difference between them is the Volhard method is a back titration. So the Volhard method is named after Jacob Volhard, and it involves the titration of excess silver nitrate. So in this titration, the precipitate, so for example, you can titrate the chloride, okay, with silver plus ions. But in Volhard titration, you would add an excess of the titrant, excess of silver plus ions. Then you would remove the precipitate, the silver chloride precipitate, and you would titrate the excess of silver with ammonium thiocyanate, for example. Okay, so in this method, this is a back titration, so you add excess of the titrant, you have to remove the precipitate, and then in a back titration, you titrate the excess of the titrant. Okay, and then you can calculate the concentration of the analyte. Okay, now in the Fayence titration, the removal of the precipitate is not necessary because it's most of the time it's a direct titration. It was developed by a Polish scientist, Kazimierz Fayence. And the typical indicator in this titration is dichlorofluorescin. So it is used as an indicator, and the endpoint is marked by the suspension in this titration changes color from green to a pink. Okay, so prior to the endpoint of the titration, the chloride ions remain in excess. They adsorbed on the silver chloride surface, and that imparts the negative charge on the particle of silver chloride. We talked about it a little bit when we were talking in general about the titration. So now, past the equivalence points, there will be, bless you, there will be an excess of silver plus ions. Okay. These ions in turn will be adsorbed on the surface, giving the particle an excess of positive charge. The difluorescin, the indicator, it's an anionic indicator. It has a negative charge, so it will be attracted to the particle of the precipitate at the equivalence point when that particle acquires a slight positive charge. Okay, and then the interaction between this indicator and the particle result in a change of the color, and that's an indication of the endpoint when the solution changes color. Okay, so these are the two most important types of the precipitation titrations that you can use to analyze all these different species. Plus, again, if your titrant is silver plus, and many times it will be because silver plus can precipitate many different ions, including chloride, bromide, iodide, and ferrocyanide ions. So that's quite commonly used titrant. And these titrations that involve silver plus ions are called argentometric titrations.